A horizon that behaves like heat suggests the universe never loses the fine print. I love that image, because a horizon is the last place you'd expect to keep records. A horizon is supposed to hide, to swallow, to draw a neat line under the past and say, that's gone. And yet, when we discovered that black holes glow with a faint thermal light, when we learned they have a temperature and an entropy, it was as if nature whispered, no, nothing is truly erased. Somewhere, somehow, the ledger at the edge is still balanced. Let me begin with the puzzle you can hold in your mind without any mathematics at all. Take a star that has burned through its fuel. Gravity wins. The star collapses. If the mass is great enough, a black hole forms, a region of space from which not even light can escape. From the outside, it looks simple, just mass, spin, and electric charge. Everything else, all the intricate details of the star and the particles that fell in, seems to be forgotten. That apparent simplicity is the seed of one of the deepest paradoxes in physics. Where did the details go? We measure details with a concept called entropy. To a physicist, entropy is not just messiness. It is a count of the number of microscopic ways a system can be arranged while looking the same to us from afar. A cup of tea has far more microscopic configurations than an ice cube, and so its entropy is higher. Now here is the startling part. In the 1970s, Jacob Bekenstein argued, and Stephen Hawking's calculation confirmed, that black holes have entropy too. In fact, the entropy scales with the area of the horizon, the surface that marks the point of no return, not with the volume inside. It is as if all the possible internal arrangements are tallied on the surface. A ledger at the edge. Why would a horizon know anything at all? Hawking showed that when we consider quantum fields in the curved space-time around a black hole, the horizon isn't a silent boundary. Quantum fluctuations mean pairs of particles flicker into being. One can fall in while the other escapes, and the escaping one is what we call Hawking radiation, a faint thermal glow. A black hole with temperature must obey the ordinary laws of thermodynamics, and with temperature comes entropy. We found heat at the edge of darkness, and heat always keeps accounts. Now, if a black hole radiates, it loses mass. Over unimaginable stretches of time, it can evaporate away. Here is the paradox sharpened to a point. Quantum mechanics insists that information is never lost. The evolution of a closed system is, in the technical sense, reversible. But if everything that fell in was smeared into oblivion, and the whole simply radiated bland thermal light, then the subtle patterns of what went in would be gone forever. That is not just untidy, it is incompatible with the quantum rules that have explained every experiment we have ever done with exquisite accuracy. So something has to give. And that something has turned out to be a profound insight about space, time, and the way the universe stores its memories. Think of a library. If you burn a book, you might say the information is lost. But if you were impossibly patient, you could chase every ash particle and photon of heat and in principle reconstruct the text. The laws do not forget. We do. With black holes, the worry was deeper, because the horizon looked like an incinerator that also sealed the chimney. Hawking's original calculations suggested perfect thermal radiation with no imprint of the past. Yet, as the decades passed, hints accumulated that the ledger is more subtle. The radiation is not perfectly featureless. It is entangled with what remains, and the pattern of that entanglement can, in principle, carry the fine print out again. There is a beautiful idea that helps here, and it has an almost poetic name: holography. In a hologram, a two-dimensional plate stores a three-dimensional scene. In certain kinds of space-time, theories of gravity seem to be exactly equivalent to theories without gravity that live on a boundary surface. The inside is encoded on the outside. If that sounds like our ledger at the edge, that is because it is. The horizon, or more generally the boundary, holds enough degrees of freedom to describe everything that fell in. Information is not destroyed. It is reorganized and written across the sky, like a watermark you only see when the light is just right. There is another helpful picture called the membrane paradigm. From the viewpoint of an observer who never crosses the horizon behaves like a physical membrane with electrical resistance, viscosity, and most importantly for our story temperature. It responds to disturbances, it rings, it conducts. This fictitious membrane is a way of doing the bookkeeping, without pretending that the interior is irrelevant. You ask, where did the information go? And the membrane replies, I have it on file. But how does the ledger get balanced in practice? How do the particularities of what fell in the pattern in the starlight, the quantum jitters of every field, come back out? One key notion is scrambling. Black holes are fast scramblers. They take any perturbation and spread its information across the whole system in a very short time. Not long in the life of a black hole, but quick compared to almost anything else in the universe. That does not mean the information is lost. It means it is hidden in correlations, like a secret shared among many friends that no single friend can reveal. The outgoing Hawking radiation, taken alone, looks thermal, but taken together in a complete set, over long times, it can encode the book that burned. All of this might sound abstract, but the last decade has made it wonderfully concrete. We have learned to compute the growth and decline of entropy for evaporating black holes using ideas from quantum gravity. Surprisingly, the curve that describes how much information is in the radiation over time. The so-called page curve does what unitarity, the quantum rulebook, demands. It rises as radiation accumulates, and then, as correlations build, it falls again, returning to zero when the whole is gone. The ledger balances. The universe does not lose the fine print. It rearranges it at the edge and whispers it back into the cold night, qubit by qubit, in patterns we are only just beginning to decipher. If that is true, then the horizon is not a bin, it is a boundary accountant. But where, precisely, are the digits kept, and how do we read them? To answer that, we need to walk from these intuitive pictures, membranes and holograms, to the modern machinery that shows how space itself keeps score, and how islands of information can appear in the most unexpected places. Islands. It is a gentle word for a radical idea, and yet it captures the feeling perfectly. Pockets of interior space that, for the purpose of keeping the books, belong to the outside. When physicists say that islands appear in the entropy of Hawking radiation, we mean that the simplest, most economical description of the information carried away by the glow includes regions behind the horizon, as if they were part of the ledger we keep at infinity. It is as if the accountant at the edge has a key to a filing cabinet in the back office, and when the accounts reach a certain stage, the cabinet quietly becomes part of the desk. To understand why this is not merely poetic license, imagine the following thought experiment. You let a black hole evaporate into a surrounding world, and you collect the radiation far away, patiently, photon by photon. Early on, the radiation looks simple and thermal. Its entropy rises because you are gathering more and more apparently featureless quanta. Then, at a special moment called the page time, named after Don Page, the balance begins to shift. The entropy of the radiation stops growing and turns over. If information is truly conserved, that turnaround must happen. Late radiation must be correlated with early radiation in just the right way to begin revealing the fine print. The modern island story shows, with a surprising elegance, how gravity itself compels this. The key tool has a forbidding name, quantum extremal surfaces, but the idea is not so terrifying. When we compute the entropy of a quantum system, we must choose a boundary that separates this from that. In a world with gravity, the cost of making that cut includes not only the ordinary quantum uncertainty, but also the area of the cut itself, because geometry fluctuates and carries information. The generalized entropy is the sum of a geometric piece proportional to area and a quantum piece that counts entanglement. Nature chooses the cut that makes this total as small as possible. Early in the evaporation, the best cut hugs the outside. The radiation is on its own, and the interior remains behind the veil. Later, a new choice wins. The optimal cut dips inside the horizon and wraps around an island. From that moment, the radiation's entropy is computed as if the island's degrees of freedom are part of the radiation. The bookkeeper has reached through the horizon and retrieved a folder. There is an even stranger twist. In the technical calculation, one uses a trick to compute entropy by making many copies of the system and then, at the end, taking a limit. In the gravitational version of this procedure, new connections, so-called replica wormholes, appear between the copies. They are not traversable tunnels you could fly through. They are stationary patterns in a path integral sculpted by the equations that tell you how entanglement threads the geometry. Their effect is to glue together the islands with the faraway radiation in precisely the way required to produce the page curve. The ledger balances because the shape of space-time in the calculation bends to make it so. It is natural to ask, is this only true in the special universes that theorists love, the ones with negative curvature and reflective walls, where holography is cleanest? The early demonstrations did indeed live in those comfortable anti-de Sitter boxes, where one can translate gravity into a quantum theory with no gravity that lives on a boundary. But the logic has grown sturdier. Toy models that evaporate into a non-gravitational bath capture the same lesson. Two-dimensional gravities, simple enough to solve, yet rich enough to teach, display islands robustly. And while the full calculus in our own expanding cosmos is more subtle, there is no perfectly understood boundary theory for our universe. The moral seems durable, when gravity can adjust the geometry of the cut. The optimal bookkeeping includes regions that lie behind horizons. What does this mean in plain terms? It means that inside and outside are not absolute when you are tallying quantum information in a world where space-time itself is dynamical. The interior of the black hole is not a separate vault with a broken lock. It is part of a larger cryptographic protocol, a code that distributes the message across the edge and the radiation. This dovetails with another deep thread, the idea that the holographic dictionary is a quantum error-correcting code. In those codes, a single logical message is stored non-locally, so that even if you lose a piece, the whole can be recovered from what remains. In the gravitational case, the entanglement wedge of a region on the boundary, everything it can reconstruct can include islands behind the horizon. So the boundary theory, which has no literal black hole, still knows about the interior, but only in a collective way that respects quantum secrecy. Notice how the metaphors conspire. The membrane at the horizon behaves like a physical system with temperature and resistance. The holographic boundary carries enough degrees of freedom to describe the bulk. The island construction tells you precisely which parts of the interior are owned by which parts of the outside for the purpose of decoding. They are different faces of a single message. Gravity organizes information at the edge. Now, if you have a mischievous streak, you might wonder whether we can use this knowledge to send someone into a black hole with a diary and have the outside world read it later, word for word, by collecting the radiation. There is a captivating thought experiment due to Patrick Hayden and John Preskill that explores exactly this mischief. Imagine throwing a secret into an old black hole, one that has already passed its page time and is maximally scrambled. They argued that after only a short delay, the scrambling time, the next small amount of radiation is already enough, in principle, to begin revealing the secret, provided you have the earlier radiation for context. The black hole, in this sense, behaves like a mirror with a delayed reflection. This is quantum chaos at its most efficient. The details are not destroyed. They are mixed swiftly and spread thinly across the outgoing light. But there is a caveat. Decoding those secrets is astronomically hard. The correlations are subtle and global. In practice, the message is safe, not because it is absent, but because nature has hidden it in a pattern so intricate that no realistic computer could unwind it. This hint that complexity itself may be a resource in quantum gravity has become a lively field, with conjectures that tie the growth of computational complexity in the boundary theory to the growth of wormhole volume or action in the bulk. The ledger at the edge may not only keep counts, it may also measure how hard it is to read the counts, and that hardness might even be the meaning of an interior that grows. All of this sounds reassuring and beautiful, but there is an unfinished question that refuses to stay quiet. If the radiation is ultimately pure, if it carries the fine print back to the universe, then what is the experience of an astronaut who falls? Is the horizon smooth, as general relativity insists, or does the accounting generate a violent firewall that burns the traveler at the edge? To follow the ledger into that controversy, we have to weigh complementarity, soft hair, and the symmetries of the sky, and decide how a peaceful crossing can coexist with perfect bookkeeping. Firewalls. It is a deliberately provocative word, and it was chosen to be so because it asks whether the universe keeps its books with such ruthless precision that it scorches anyone who dares to cross the boundary. The argument, devised by Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, often shortened in the literature to AMPS, begins with a simple quantum principle called the monogamy of entanglement. If two systems are maximally entangled, they cannot also be maximally entangled with something else. Early in evaporation, each outgoing Hawking quantum is entangled with its partner that fell just inside the horizon. Later in evaporation, to restore purity and produce the page curve that turns over and falls, the new radiation must be entangled with the old radiation outside, not with a fresh partner inside. The monogamy rule seems to force a choice. Either the horizon is smooth for the infalling astronaut with interior partners intact, or the outside world recovers the information. You cannot have both. If you insist that the outside recovers every last qubit, the horizon, they argued, must become a furnace, a firewall that breaks the entanglement and burns the traveler. Now, I do not like horizons that burn. General relativity teaches that a sufficiently large black hole is locally dull at its edge. If you free fall across, you should feel nothing, at least for a while. This is the equivalence principle. That deep insight of Albert Einstein in free fall gravity disappears. Many of us felt that a firewall, while logically crisp, was physically offensive. So we asked, have we smuggled in an assumption that fails in gravity? The most famous candidate is complementarity, introduced by Leonard Susskind and Gerard Hooft in the 1990s. It says in essence that no single observer can witness a contradiction. The outside observer can describe every process as if it took place on or just outside the horizon. The infalling observer can describe a smooth passage through. Each story is self-consistent, and because no one can both hover for eons to collect the radiation and also jump in, there is no operational conflict. In complementarity, the universe keeps two ledgers that agree wherever they must agree, even if they look different on separate desks. But the AMPS argument pressed harder. Even without a single observer performing both feats, the mathematics of entanglement seem to force the dilemma. That is where the last decade's island machinery quietly alters the stage settings. With islands, the interior partners of late Hawking quanta can, in the sense of entanglement wedge reconstruction, be part of the algebra of operators that the outside radiation can recover after the page time. There is no need to break entanglement at the edge. Rather, the bookkeeping reassigns who owns which degrees of freedom. The interior mode that an infalling astronaut would call mine is for the distant decoder a code word written non-locally across the early radiation. In this picture, the horizon can remain calm while the ledger still balances. The paradox does not vanish, it changes address. The question becomes, how does the universe implement that non-local code in a way that preserves the peaceful crossing promised by Einstein? Here is one suggestive hint: gravitational dressings. In a theory with gauge symmetry and gravity is a kind of gauge theory of spacetime itself. There are no strictly local, gauge-invariant operators. To create a particle, you must attach a string of field that reaches to infinity or to a boundary, because charges and masses source long-range fields. The operator that adds a quantum just inside the horizon is not confined to a point, it trails a thread that touches the edge. In that sense, the inside and the outside are never strictly separable to begin with. The apparent contradiction in the AMPS setup leans on a notion of locality that gravity gently refuses. The island story formalizes that refusal. The optimal cut for entropy computation bends to include the interior region necessary for consistent entanglement. There is another, more down-to-earth line of thought with a rather charming name: soft hair. Stephen Hawking, Malcolm Perry, and Andrew Strominger argued that black holes are not as bald as the classic no-hair theorems would have us believe. At null infinity, where light rays end up, the universe's gravitational field enjoys an infinite family of subtle symmetries, the Bondi-Metzner-Sachs symmetries, named after Hermann Bondi, M.G.J. van der Burg, A.W.K. Metzner, and Rainer Sachs. Associated with these symmetries are conserved charges carried by ultra-low energy or soft gravitons and photons. When matter falls in, it leaves a permanent memory in the pattern of these soft modes. In gravitational wave astronomy, we call a related effect the memory effect, a lingering displacement of test masses after a burst of waves has passed. Soft hair suggests that even classically, there are ledgers written on the sky detailing who crossed the horizon and when. They are very hard to read because soft charges are spread thin and are gauge-like, but they expand the notion of what counts as hair. They do not, by themselves, solve the quantum information problem, but they reinforce the theme: the universe scribbles in more places than we used to think. A bolder proposal from string theory goes further still. Perhaps there is no traditional interior at all. In the fuzzball program, largely developed by Samir Mathur and collaborators, each black hole microstate is a horizonless, complicated configuration of strings and brains that, on average, mimics a classical black hole at a distance but never develops an empty interior. If that is right, the ledger is literally the geometry, the surface is where the microstate lives, and radiation can be non-thermal from the start. It is a striking idea, and in certain supersymmetric, highly symmetric toy models, fuzzball constructions exist. Whether they exist for the astrophysical holes in our sky remains uncertain, but the message is again familiar. Microstates matter, and they may rearrange what we mean by inside. Between complementarity, islands, soft hair, and fuzzballs sits an elegant, almost whimsical equation proposed by Juan Maldacena and Leonard Susskind: ER equals EPR. Einstein-Rosen bridges, which are non-traversable wormholes connecting two regions of space, might be the geometric counterpart of Einstein-Podolsky-Rosen entanglement, the quantum correlation that scandalized Einstein in the 1930s. If entanglement can be thought of as a kind of wormhole, then the growth of entanglement could literally be the growth of interior geometry, and decoding the radiation might be the same as manipulating a network of quantum connections that, in a dual description, looks like a wormhole network. This is not a literal tunnel we can fly through. It is a way of thinking that turns accounting into architecture. The ledger at the edge is a set of bonds that hold space together. Where does this leave the traveler? If I were brave enough to dive in, would I feel heat? The most conservative expectation remains: for a sufficiently large, unperturbed black hole, the horizon is smooth. The bookkeeping that ensures purity is carried out in structures that do not announce themselves locally. You glide through, and only when you approach the singular region do tidal forces become fatal. Yet there is a cautionary note. The peaceful horizon relies on conditions about the state. No one outside has performed an impossibly precise, malicious decoding that would project the radiation onto a basis that breaks the entanglement you need for a calm crossing. In principle, a demon with cosmic computing power could create a drama at the edge. In practice, the universe hides the keys behind complexity walls so steep that no mortal mind can climb them. The books are balanced, and the door remains soft. Still, the story's not finished, and I find that wonderfully human. We have models where islands reproduce the page curve. We have hints that complexity growth mirrors the swelling volume of wormholes. We have symmetries on the sky that promise faint, permanent memories. To bind these threads into a single, predictive framework for the holes in our own universe, the ones photographed by the Event Horizon Telescope and weighed by the Laser Interferometer Gravitational Wave Observatory, we need to connect microscopic bookkeeping with macroscopic observables. Can we hear the ledger in the ringdown of a newly merged whole? Could the polarization pattern near the horizon betray the presence of near-edge degrees of freedom? To chase those possibilities, we must step from paradoxes to phenomenology, from the chalkboard to the sky, and ask what a ledger sounds like when gravity sings. When gravity sings, it does so in overtones. After two black holes collide and settle, the newborn horizon rings like a struck bell. We call those notes quasi-normal modes, damped oscillations whose frequencies and decay times are determined solely by the final hole's mass and spin. That is already a remarkable statement, because it tells me that the ringdown is a fingerprint of the ledger's outer cover area, an angular momentum rather than a diary of the messy details that came before. But there is a second, subtler hope that keeps theorists awake at night. If the horizon is more than a mute surface, if there are near-edge degrees of freedom that keep the books, then tiny departures from that pristine spectrum might lurk in the tail of the song. Not a shout, just a whisper. Extra lines in the spectrum, faint beats, delayed echoes. I would not bet my life on hearing them soon, but searching is how physics learns what to ignore and what to treasure. What would we be listening for? Start with the most conservative test. Does the horizon obey an area law in violent events we can actually observe? In classical general relativity, the total area of horizons cannot decrease. If the final ringdown and the in-spiral chirp are measured cleanly enough, you can infer the areas before and after and ask, did the ledger add up? Early analyses suggest that nature plays fair, but we want many more events and sharper ears. Passing such tests does not resolve paradoxes by itself, yet it builds confidence that the thermodynamic portrait temperature, entropy, balance sheets at the edge belongs to the real sky and not just to our notebooks. Beyond the area test lies spectroscopy. If the ledger were to write in a different hand near the edge, one speculative signature is a late-time echo, a series of faint, evenly spaced pulses following the main ringdown, as if some structure close to the horizon reflected a small fraction of the waves back and forth. Claims have come and gone, the data are delicate, the background's tricky, and confirmation demands patience and humility. Another possibility is that additional near-horizon physics shifts the frequencies of the overtones ever so slightly from the predictions of Einstein's theory. Again, the right attitude is one of quiet curiosity. We set up the experiment, we let nature speak, and we listen without forcing an answer we already prefer. Phenomenology is not limited to gravity's audible range. The Event Horizon Telescope, by imaging the flow of plasma and magnetic fields near the brink, gives us a different kind of stethoscope. In those polarized maps, the membrane paradigm ceases to be a mere pedagogical trick and becomes an engineering language for the cosmos. You can treat the horizon as if it had a surface resistivity and a finite conductivity. You can model how fields anchor on it, how currents close, how energy is extracted to power jets. None of that tells you directly about islands or replica wormholes, but it grounds the notion that the edge behaves like a physical system, a place where transport, dissipation, and response are meaningful words. And then there is memory gravity's soft whisper that never quite fades. When a burst of gravitational waves passes a pair of freely falling test masses, it leaves a permanent displacement, however tiny. That is the gravitational memory effect, a classical cousin of the quantum soft hair idea. Think of it as a faint crease ironed into space-time by the wave's passage, a bookkeeping mark that says an event occurred. Detecting memory robustly is hard, because it is a step change rather than an oscillation, and instruments are happiest with wobbles. But the physics is clean, and the concept is exquisite. The sky keeps a minute, ineradicable note of who accelerated where. If black holes are accountants, memory is the stamp they use when the ink is almost gone. I find it helpful, when the observational threads feel fragile, to return to the deeper unity behind them, the thermodynamics of space-time. Ted Jacobson showed something breathtaking in its simplicity. If you assume that every local patch of a null surface behaves like a horizon with a temperature proportional to its acceleration, and you demand that the Clausius relation heat equals temperature times change in entropy hold for all such patches, then the field equations of general relativity fall out as an equation of state. In plain terms, gravity looks like the hydrodynamics of many unseen degrees of freedom. The area law becomes an entropy density. The equations that tell planets how to move read like the constitutive relations of a medium. That is precisely the spirit of our ledger. Macroscopic balance laws emerge from microscopic bookkeeping we do not yet fully see. The holographic dictionary sharpens the sentiment. The Ryutaka-Yanagi proposal and its quantum generalization say that the entanglement entropy of a region in the boundary theory equals the area of an extremal surface in the bulk plus quantum corrections. Entanglement becomes geometry. Geometry becomes entanglement. The page curve calculations with islands are then not miraculous one-offs, but natural consequences of the same principle. When you ask about the entropy of Hawking radiation, the extremal surface you should choose sometimes dives behind the horizon, and the area term dutifully records the ledger's page count. If the area shrinks as the whole evaporates, the radiation's entanglement grows and then declines in just the right way. The book is never burned, it is rebound with a new cover. There is an irresistible modern twist to all this: complexity. In quantum field theories, with many degrees of freedom, states become hard to describe, not because the information is gone, but because the most economical circuits that prepare them are long. Holography offers geometric duals to that circuit depth conjectures, with names that are as plain spoken as they are profound. Complexity equals volume. Complexity equals action. As a black hole interior grows linearly for a long time after formation, the boundary state's complexity grows too. It is as if the universe measures the difficulty of decoding its own diary and translates that difficulty into the expansion of an interior that no one can visit and return from. The ledger does not just count, it ages. One may ask, rightly, whether we are being seduced by metaphors. Ledger, membrane, code, wormhole, memory, are these just comforting words we swap for the harsh calculus we cannot do? That is a fair concern, so let me be precise about their role. Metaphors in physics are scaffolding, not facades. we erect them to climb toward equations. They are worthwhile only when they lead to predictions we can test or to calculations we can check against each other. Islands are not a turn of phrase, they are a prescription that reproduces the page curve. Membranes are not an after-dinner analogy. They are a boundary condition that reproduces astrophysical electrodynamics near horizons. Codes are not a literary flourish. They are the exact structure that makes bulk operators reconstructible from boundary data. When the scaffolding keeps leading to firm floors, you start to suspect there is a building. If all of this is right, if the horizon keeps accounts, if interior and exterior are partners in a non-local orbit, then a strange, beautiful question arises. Where else does the universe keep books in this way? Do de Sitter horizons, the cosmological horizons of an accelerating universe, carry a similar ledger for everything beyond our view? Does the entropy of our observable patch play by the same rules, with islands that peak beyond the veil? To approach that, we have to leave the comfortable boxes where holography is sharp and ask how to write a dictionary for a world that looks like ours, expanding, messy, and full of galaxies. That is the next frontier, because if the bookkeeping at the edge is truly a universal habit of space-time, then it touches not only the fate of stars, but the origin and arrow of time itself. And that takes us from the quiet of black holes to the first light of the cosmos. From the first light, let us step to the far edge of sight. Our universe appears to be accelerating, driven by something that behaves like a tiny, uniform pressure in empty space. In such a world, every observer carries a private horizon, the farthest distance from which light, sent now, could ever reach them. This boundary is not a wall built of matter, it is a limit set by expansion. And like a black hole horizon, it too hums with a faint thermal character. Gary Gibbons and Stephen Hawking showed that an observer in a steadily accelerating, nearly de Sitter cosmos perceives a temperature associated with that cosmic horizon and an entropy proportional to its area. So once again, nature lays out a ledger at the edge, a count of hidden microstates written not in volume but in area. That is a striking refrain. Whether we are falling into a collapsed star or watching galaxies drift apart, the universe insists that boundaries keep the books. If that is more than a coincidence, if it is a principle, then horizon thermodynamics is not a curiosity, but a grammar. It says, where there is a limit to what you can see or signal to, there is an entropy. Where there is an entropy, there is a temperature. And where there is temperature, there is a notion of heat flow. Ted Jacobson made this precise in a beautiful argument that reads almost like a haiku of physics. Assume that every little patch of a light-like surface behaves like a tiny horizon. Demand that heat equals temperature times change in entropy for the matter that crosses it. And out tumble Einstein's equations, not as divine commandments, but as an equation of state. Space and time behave like a medium with many unseen constituents. Their large-scale dynamics are the hydrodynamics of information. If horizons keep accounts, might our own cosmic horizon tally the fine print of everything that slips from view as the expansion carries it beyond our reach? That is a delicate question. Unlike the comfortable anti-de Sitter boxes beloved by theorists, our universe does not present a clean boundary where one can write a dual theory free of gravity. The dictionary is smeared and incomplete. Even so, hints accumulate. The static patch seen by any one observer looks like a finite thermal system with an entropy proportional to the horizon area. In such a finite system, one expects recurrences over truly astronomical times, and a limited capacity to store novelty suggestions that are as unsettling philosophically as they are tantalizing physically. Some have argued for a kind of de Sitter complementarity, in which no single observer can collect contradictory accounts of what the horizon has recorded. Others explore island, like constructions in cosmological settings, where the optimal way to compute entanglement, entropy of the radiation, inside one's patch includes regions that, in a global sense, lie beyond it. The details remain unsettled, but the melody is familiar. Gravity bends the bookkeeping surface to keep the ledger consistent. Closer to home, there is a horizon each of us can build with nothing more than a rocket. Accelerate hard enough for long enough, and the space-time behind you becomes inaccessible. A Rindler horizon appears. Even that artificial edge comes with a temperature, known as the Unruh temperature, a warm breeze felt by an accelerated detector drifting through what an inertial observer calls vacuum. It is another reminder that horizons are not merely astrophysical ornaments, they are a universal response of quantum fields to limits of access. Where you cannot look, the universe assigns an entropy. Where you cannot send a message, the vacuum is warmer than you thought. The ledger is not only at infinity, it is wherever ignorance becomes irreducible. There is a deeper moral here, about the arrow of time. We experience time as a flow from past to future. Tea cools, stars burn, eggs break. The orthodox explanation is statistical. The microscopic laws are reversible, but the universe began in a special low entropy state, and the subsequent growth of entropy is simply the most probable evolution from that beginning. Black holes complicate the story by offering the highest entropies nature can afford for a given region. A collapsing star can increase entropy enormously by becoming a hole. Evaporation can, in principle, return that entropy to the wider world without destroying information. Cosmological horizons add a further twist. If the area of the horizon measures the entropy of what an observer can ever access, then the accelerating expansion sets a kind of ceiling on accessible entropy, even as the total entropy in all that exists may continue to grow. Meanwhile, in the holographic language, computational complexity, how hard it is to describe the state, may grow long after entanglement entropy is saturated. In that sense, the universe can look thermally old while remaining computationally young. The ledger balances, but the arithmetic becomes harder to read with every tick. We should be honest about how much we do not yet know. In black holes, string theory has provided sharp microstate counts for special supersymmetric cases, matching the Bekenstein-Hawking entropy beautifully. In more general settings, we do not yet have a complete accounting. In cosmology, we do not possess a clean, boundary quantum theory that everyone agrees describes our sky. The island story, so crisp in evaporating toy models and in anti-de Sitter contexts, is still being adapted carefully to expanding spaces. And the notion that the Hilbert space of a de Sitter patch is finite raises profound puzzles about locality, causality, and the fate of quantum coherence over unimaginable timescales. These are not roadblocks, they are signposts, telling us our metaphors are approaching their load limits and fresh mathematics is required. Yet even while the fundamentals are debated, the universe gifts us with ledgers written in light. The cosmic microwave background, the afterglow of the hot early universe, is a fossil record of quantum fluctuations, stretched by inflation, imprinted on the sky as tiny temperature differences, and polarization swirls. It is, quite literally, a page from an ancient account, a map of correlations that reads like the minutes of a meeting between gravity and quantum mechanics. If we could detect the primordial gravitational waves that inflation might have generated, we would be hearing another entry in that book, a soft chord echoing across the ages. Each such measurement constrains the grammar that any complete ledger must obey. Where does this leave our question? If horizons behave thermally, and if entanglement weaves geometry, then black holes are not erasers, but encoders. Their edges are not places where stories end, they are places where stories are compressed, scrambled, and given patience and impossible finesse, can be told again. The cosmic horizon may do something similar for the part of the universe we will never touch. not deleting, but redacting, storing what lies beyond in a code that our local physics cannot easily read. The picture that emerges is humbling. The universe never loses the fine print. It files it under beyond your current access level, and it ties the folder shut with threads of entanglement. That raises a natural, almost childlike curiosity. What exactly are the microscopic letters that fill these pages? What are the degrees of freedom whose count gives an area divided by 4 in Planck units? Are they strings and brains, loops and spins, or something we have not named yet? To follow that curiosity, we must leave the macroscopic poetry of horizons and step closer to the grain of space-time, toward the statistical mechanics behind the area law, and toward concrete microstate pictures that show how a smooth exterior can emerge from a seething quantum interior. When you ask what the microscopic letters are, you are really asking for a dictionary, a way to list the individual degrees of freedom that add up to the black hole's entropy, which is 1/4 of its horizon area in Planck units. The fact that the count goes with area, not volume, is the first clue that these letters live at or near the edge. And over the past half-century, several independent grammars have appeared, each illuminating a part of the page. String theory offered the first fully controlled spelling lesson. In certain highly symmetric cases extremal, very cold black holes with carefully balanced charges. Andrew Strominger and Kumran Vafa showed that you can literally count the microstates as bound configurations of strings and brains. You do the combinatorics in a world where the calculation is clean, and then you relate the answer to the area of the corresponding black hole. Miraculously, the numbers agree. The logarithm of the count equals the area divided by 4, at least in those idealized cases. Later, Ashok Sen refined the story to include quantum corrections, and again the ledger balanced. This is not yet a census for the messy spinning holes in our telescopes, but it is a proof of existence. There are enough microstates, and they can be counted. And the book of the horizon is not an empty notebook. Loop quantum gravity approaches the page from a different angle. In that framework, geometry itself is quantized. Area and volume come in discrete quanta. A black hole horizon is pictured as a surface pierced by spin-networked links, each puncture contributing a little quantum of area. Count the ways those punctures can be arranged while respecting the rules, and you get an entropy proportional to the area. The proportionality constant depends on a parameter, the Barbero-Immirzi parameter, that is fixed, in practice, by requiring the coefficient to match 1/4. Critics will say that feels like setting the answer and working backward. Defenders will point out that the structure behind it is robust and that the emergence of an area law is striking in itself. Either way, the message is consonant. There is a finite set of edge degrees of freedom, and their combinatorics reads like a ledger. There is also a beautifully minimalist route based on symmetry. Near any non-extremal horizon, the physics simplifies, and one can argue that the relevant modes furnish a two-dimensional conformal symmetry of Virasoro algebra with a central charge. If that is so, then a universal formula from two-dimensional statistical mechanics, the Cardi formula, computes the entropy purely from symmetry data and reproduces the area law. This line of thought appears in different guises, from horizon CFT to the Kerr/CFT correspondence for rapidly spinning holes, and while the technical foundations are debated, the aesthetic is irresistible. Perhaps the bookkeeping is enforced by symmetry alone, and the ledger is a consequence of the way the universe insists its edges transform. Yet another, very down-to-earth thread is the role of boundaries in gauge theories. In a theory with gauge symmetry, you cannot cleanly split space into two regions without paying a price. To make observables that live entirely on one side, you must introduce additional edge modes at the cut so that the gauge constraints are satisfied. Those modes carry entropy. In gravity, where diffeomorphism invariance plays the role of a gauge symmetry of spacetime itself, one expects the same phenomenon in a more subtle form. A natural speculation is that the area term in the entropy is, at least partly, the entropy of these gravitational edge modes, renormalized into Newton's constant. On this view, the ledger at the edge is not optional bookkeeping. It is demanded by the very grammar of the theory. All these perspectives agree on something profound. Horizons are thermodynamic because there are microscopic degrees of freedom, and the area counts them. But a good thermodynamic theory does more than count. It gives transport coefficients and response. Here, the membrane paradigm and holography meet in a lovely piece of universality. Treat the horizon as a fluid with a shear, viscosity. In a wide class of strongly coupled quantum field theories that possess a clean holographic dual, you find that the ratio of shear viscosity to entropy density equals 1 divided by 4 pi, a value so small that it was conjectured to be a lower bound. Whether nature saturates that bound universally is still discussed, but the existence of such a simple ratio ties the whisper of near-horizon physics to the roar of quark-gluon plasmas in heavy ion collisions. The same mathematics that keeps the ledger flat also governs how quickly disturbances are smoothed out. Even the area divided by 4 gains nuance beyond Einstein's theory. In gravity theories with higher curvature corrections, the right entropy is not simply the area. It is given by a more general expression due to Robert Wald, a Noether charge associated with diffeomorphism invariance, evaluated at the horizon. In string theory, those corrections appear naturally, and the microstate counts continue to match Wald's formula. The lesson is that the ledger's column headings are theory-dependent. What looks like area, in the simplest theory, becomes a more intricate, functional, in a richer one. But the logic entropy as a boundary charge that counts microstates survives. There is a modern bridge between the microscopic and the macroscopic that I find particularly compelling: the fluid gravity correspondence. Small, long wavelength perturbations of a black brain, a planar cousin of a black hole map, precisely to the equations of relativistic hydrodynamics in one fewer dimension. In other words, the near-horizon dynamics behaves like a fluid, and its viscosity, conductivity, and diffusion constants can be read off from horizon data. That is the membrane paradigm elevated to a derivation, not a metaphor but a duality. The accountant at the edge doubles as a fluid mechanic, and the same symbols on the page are both entries in a book and eddies in a flow. What about the interior's timekeeping its steady growth long after the exterior has settled? Here the language of quantum information leans in. If complexity, the minimal number of simple gates required to build the state, grows for a time that is exponential in the number of degrees of freedom, then the dual geometry's interior grows linearly over correspondingly long times. Toy models like the Sachdev-Yekitayev model, many fermions with random all-to-all interactions, display maximally fast chaos and have gravitational duals in simple two-dimensional dilaton gravities. In those laboratories, the page curve can be computed, islands can be drawn on paper, and the growth of wormhole volume mirrors the growth of computational complexity. None of this replaces the sky. All of it trains the ear to hear what kinds of ledgers quantum gravity prefers to keep. You may notice a pattern in this tour. Every successful account of horizon entropy smuggles in, openly or otherwise, 3 recurring motifs. First, a boundary, a place where you slice the world into owned and not yet owned. Second, symmetry, a set of transformations that constrain what the edge can do and sometimes determine everything. Third, statistics, a very large number of microstates whose collective behavior is smooth. Put those together, and the area law is less a miracle than a law of large numbers applied to geometry. The ledger is the law. Still, a responsible storyteller must admit there are puzzles untouched. For astrophysical, rapidly spinning, hot black holes, we do not yet possess a full microstate census that is both explicit and general. We can compute the leading term and some corrections from symmetry and from holography. We can match special cases in string theory. We can model code like reconstructions of interior operators from exterior data. But a complete dynamical picture that runs from collapse to evaporation, with every qubit traced and every clause of the ledger checked, remains a goal rather than a possession. That is why the next step is so important. To connect the microphysical stories, strings, loops, edge modes, codes, to concrete falsifiable signatures in the data we gather from merging black holes, glowing accretion flows, and perhaps one day from quantum sensors that can feel gravity's softest hairs. To walk that path, we need laboratories where the bookkeeping can be rehearsed and judged, simpler worlds in which we can compute both sides of the dictionary and then carry the moral back to our sky. Those worlds already exist, from two-dimensional gravities to chaotic quantum many-body systems whose scrambling we can measure. Let us visit one of them now. A small theatre where islands appear on cue, wormholes are drawn as diagrams, and entanglement is geometry you can hold in your hands. In the small theatre, the sets are drawn with a single stroke. I am thinking of a toy world that keeps the essence of gravity while stripping away the clutter. A two-dimensional stage where time and one slice of space are all that exist, and a gentle dilaton field shapes the curvature. On that stage, we can write every line of the play. Black holes form and evaporate. Entropy rises and falls along a clean page curve. Islands appear at precisely the moment the accounting demands them. And because the mathematics is kind, we can follow the ink as it moves from one side of the ledger to the other. There is a companion laboratory, a many-body quantum system, that looks nothing like gravity at first sight. Imagine a large number of fermions, each one able to talk to every other, with couplings chosen randomly, but held fixed once drawn. It is chaotic, but not mischievously so. It is maximally efficient at scrambling information. Left to itself, a sharp disturbance is blurred into the whole, in the shortest allowed time, a logarithmic heartbeat compared to the system size, and yet, astonishingly, the late time, low energy behavior of this unruly model mirrors the gentle two-dimensional gravity on our other stage. The same simple reparameterizations of time govern both. The same soft mode dictates how correlation functions decay. The same kind of wormhole saddles appear when we compute averages over many realizations. Two plays, one scriptwriter. In these paired theatres, we can rehearse the paradoxes until they lose their snarl. Take the radiation from an evaporating black hole in the gravitational play. Early on, the best description of its entropy is mundane. Count the entanglement outside, keep the inside separate, the number grows. But as the quanta pile up, a new geometric cut wins the extremization game. It dips behind the horizon and circles an island that had previously belonged to the interior. From that moment, the radiation's entropy is computed as if the island's degrees of freedom were already yours. If you sketch the curve, you see it turn over and glide back towards purity. It is satisfying in the way a solved puzzle is satisfying, not because the world became less mysterious, but because the mystery found its proper frame. On the many-body side, you can perform a parallel audit using replica tricks and ensemble averages. When you compute the entropy of a large subsystem, saddle points in a replicated path integral connect different copies, and those connections look, in the dual picture, like wormholes. These are not tunnels one could traverse with a spaceship. They are quiet, Euclidean patterns that tell you how entanglement threads the space of states. Their presence lowers the entropy in precisely the way that reproduces the page curve. The island in gravity is the wormhole in the replicates. The moral is the same. The ledger balances when you allow geometry to participate in the book closing. Because the theaters are solvable, we can also test bolder ideas about sending and receiving messages across the edge. There is a thought experiment I find irresistible because it feels like a conjurer's trick explained. Suppose you prepare two quantum systems in an entangled state that in the gravitational picture looks like two black holes joined by a non-traversable Einstein-Rosen bridge. In the plain story, nothing goes through. The bridge is a mirage. But with a carefully chosen, very small coupling between the two boundary systems, a coupling that looks like a simple product of operators, you can render the bridge momentarily traversable. A signal thrown into one side emerges on the other. In the dual language of the laboratory, you performed a transparent version of quantum teleportation. You used shared entanglement and a small, well-timed operation to move a message. In the gravity picture, the ledger at one edge spoke to the ledger at the other, and the book's binding briefly became a corridor. What matters is not the spectacle, but the accounting. The coupling injects negative energy into the throat, opening it just enough for a whisper to pass. Causality is not violated. You needed the entanglement in place from the start, and you engineered the nudge with exquisite timing. The point is conceptual. Entanglement is not a decorative bow on the story. It is the architecture. The same resource that restores purity to Hawking radiation also permits, in allied setups, the controlled transmission of information where naive reasoning would forbid it. Ledgers, codes, and bridges are three views of the same mechanism. These models also let us put numbers on ideas that otherwise live as metaphors. Consider scrambling. If a black hole is a fast scrambler, the time it takes to mix a small perturbation into the whole grows only logarithmically with the entropy, which itself is proportional to the area. That is breathtakingly swift. In the many-body theater, you can watch scrambling by following an out-of-time ordered correlator, a diagnostic that measures how a small poke here affects a measurement there after some evolution. It begins gentle, and then, at a time set by that logarithm, it falls off rapidly, signaling the butterfly effect made quantitative. In gravity, the corresponding story is a shockwave that shifts geodesics near the horizon ever so slightly, producing a large effect on the return time of probes. Two languages, one behavior. The books are mixed quickly, but not randomly. They are mixed as fast as quantum mechanics permits. A subtlety that these stages bring into focus is the role of complexity. Entanglement entropy grows and then saturates. In an evaporating setup, it turns over and declines. Complexity, by contrast, keeps climbing for a very long time. In the gravitational story, this is mirrored by the volume or action of a wormhole interior that grows linearly long after exterior observers see only a quiet, settled horizon. It is as if the interior is a physical manifestation of the difficulty of rewriting the global state in a simple way. The geometry ages not because new information is being created, but because the accounting problem is becoming harder. If the ledger is the area term, complexity is the thickness of the book's spine. Even teleportation can be given a complexity twist. You can, in principle, decode a diary that fell into an old black hole by collecting the radiation and performing an astronomical computation. Or you can engineer an entanglement-assisted protocol in which a modest operation designed with knowledge of the shared structure allows a message to emerge with far less effort. On the gravity side, the difference looks like the gap between tunneling through the rock and persuading the mountain to open a door for an instant. In either picture, the crucial resource is not brute force, but the right correlation set in advance. I find comfort in the way these toy worlds treat the audacious and the mundane with the same mathematics. Islands and wormholes sound romantic, extremal surfaces and replica saddles sound austere. But they are the same objects seen with different lighting. And because they are calculable, they let us test our slogans against stern integrals. When the slogans survive, we keep them. When they do not, we file them away with gratitude and move on. What then do these rehearsals teach us about the sky? They say that if we want to hear the ledger in real data, we should listen for signatures of fast scrambling in ringdowns, for the universal transport of near-horizon fluids, for the whisper of memory and gravitational wave baselines, and for the way polarization close to the brink encodes ordered fields that a membrane-like horizon can support. They also caution humility. Decoding the universe's diary is hard, not because the diary's burned, but because its cipher is a code written across the whole. And there is a final lesson, one that reaches beyond black holes. If entanglement can be geometry, if complexity can be interior growth, then perhaps the special initial conditions of our cosmos, the curious low entropy beginning from which our arrow of time flows, are themselves a statement about how the first ledgers were written. To explore that, we must leave the toy stages and walk back into the bright foyer of cosmology, where inflation, reheating, and the birth of structure await, and ask whether the same bookkeeping that balances a dying star's accounts also set the terms of the first morning's light. If the first morning's light carries an account, it is written in a remarkably tidy hand. Inflation, that brief epoch of almost exponential expansion, takes whatever messy initial patchwork there may have been and smooths it, stretching space so quickly that wrinkles are ironed flat and relics are thinned to invisibility. In such a state, the universe looks locally like de Sitter space, with a horizon that has a temperature and an entropy proportional to its area. Once again, a boundary appears. Once again, thermodynamics whispers that where access is limited, nature keeps a ledger. But there is a deeper subtlety here that I find quietly beautiful. Inflation both erases and writes at the same time. It smooths the large scales so that gravity's unruly degrees of freedom begin in a tame, low-entropy configuration, and yet it also amplifies the tiniest quantum jitters into classical seeds of structure. It clears the blackboard and then chalks the first lines. Roger Penrose taught us to think of gravitational entropy not simply as heating gas, but as the degree to which space-time's curvature is clumped and knotted. A perfectly smooth geometry has extraordinarily low gravitational entropy. A universe broken into galaxies and stars and black holes has far more. On that view, the beginning must have been special, the past hypothesis, as philosophers of physics like to call it, and inflation, whatever its dynamical origin, is a mechanism that takes a small, smooth patch and makes it big, preserving that specialness over an enormous domain. The arrow of time we feel in our tea and our memories then flows because entropy can grow from that gentle start. The ledger was nearly empty at dawn, and there was room to write. And what did the early universe write? Tiny, nearly scale-invariant fluctuations in density and temperature, born from quantum fluctuations of a field, stretched by inflation to cosmic sizes. These are not hand-waving stories. They are precise, statistical predictions. The quantum state of those fluctuations is a squeezed vacuum, a peculiar arrangement in which uncertainties along one combination of variables become very small, while the complementary combination is correspondingly large. As modes cross the inflationary horizon, that temporary edge, beyond which they cannot communicate, their quantum correlations are frozen into classical patterns. Later, as the universe reheats, those patterns become variations in the temperature and polarization of the cosmic microwave background, and still later, the butterflies of structure that grow into galaxies and clusters. The ledger at the inflationary edge is the power spectrum and the subtle cross-correlations we map on the sky. It is an accountant's chart with ripples. The act of freezing in these correlations is often described as decoherence, and I think that is the right language. Not a mystical collapse, but an ordinary bleeding of quantum phases into inaccessible degrees of freedom as modes become causally separated. Each Hubble patch carries its own partial record. No patch has the whole story, but together the sky holds a consistent book. And because the statistics are so close to perfect Gaussianity, we can ask delicate questions. Are there tiny non-Gaussian fingerprints that betray the details of the inflating field or its interactions? Are there isocurvature components that hint at additional actors on the early stage? Every answer tightens the binding of the ledger. Then comes reheating, a name so homely for a process so violent. The energy stored in the inflating field decays into particles and radiation. The universe becomes a hot plasma. Entropy explodes upward. It can sound at first hearing like a feast of forgetting, a chaotic bonfire that would erase the neat inflationary script. But that is not how quantum mechanics works. The statistical distributions we plot in textbooks emerge precisely because a pure, exquisitely correlated state evolves into one whose local pieces look thermal. Unitarity, the rule that information is never destroyed, means the fine print is not burnt. It is dispersed into correlations that no local experiment can read in full. We see the average letter forms even as the full manuscript remains written in an alphabet of entanglement running across the whole sky. There is a tantalizing echo here of the black hole story. During inflation, there is a horizon with an associated temperature. Modes cross it and become part of what you might call the outside book. Later, they re-enter our horizon in the decelerating universe and write their lines into the microwave background and the large-scale web. If one applies the island intuition naively, one is led to ask whether the optimal bookkeeping surface in certain cosmological entropy questions might dip beyond our accessible patch, effectively annexing regions we cannot observe. The details are technically subtle, and our cosmos is not a neatly boxed anti-de Sitter laboratory, but the melody is the same. When geometry can flex, the boundary that keeps the books is not fixed. It moves to make the account consistent. Of course, there are puzzles. De Sitter space seems to possess a finite entropy associated with its horizon area. If that is literally the number of microstates accessible to a single observer, then the Hilbert space, describing a cosmic patch, might be finite dimensional. That is a radical notion, one that raises hard questions about recurrences and about how to define observables over unimaginable times. Some physicists argue for a de Sitter complementarity in which no single observer can test conflicting descriptions, much as with black hole horizons. Others suggest that truly global descriptions evade such finiteness. The debate is lively, and I am content to let it be so. The right principle, once found, will unify our treatments of black holes and of the cosmic horizon into one grammar of edges. Meanwhile, the sky continues to adjudicate. We look to the faint curl pattern in microwave background polarization, the so-called B modes, as a potential signature of primordial gravitational waves, a soft chorus from inflation's quantum origin. We map large-scale structure ever more finely to test the Gaussianity and scale dependence of the initial fluctuations. We listen, with increasingly sensitive interferometers, for a stochastic background of gravitational waves, from phase transitions, or from cosmic strings. Speculative, yes, but testable in spirit and in practice. Each measurement is a question posed to the early ledger. What did you write? With what ink? And on what kind of paper? There is also the possibility that inflation left denser entries in the margins, primordial black holes born from rare, large fluctuations. If they exist in abundance, they could contribute to dark matter or seed supermassive black holes. If they are rare, they are still conceptually delicious because they would carry an information account that began almost at the birth of time. Constraints from microlensing, from accretion effects, and from gravitational waves already fence in large swathes of parameter space, but a small corner remains open in some mass ranges. Here too the etiquette of ledgers applies. Their formation, growth, and potential evaporation must respect the accounting rules we have been exploring all along. All this talk of writing brings me to a quiet but important point. When we say the universe stores or keeps information, we are not implying a cosmic clerk with shelves and folders. We are saying that the laws are reversible and that the correlations that define a state never vanish. They merely become difficult to access. The difficulty can be quantifiable in circuit depth, in the growth of wormhole interiors, in holographic jewels, in the spread of influence measured by out-of-time order correlators. The arrow of time is then not the universe forgetting. It is the universe writing in a hand that becomes progressively harder to decipher. The book grows thicker, the ink grows finer, the pages keep turning. To bring these themes down from the first light to experiments we can touch, I want to step into laboratories where horizons are engineered and thermality emerges in the strangest places, superfluids and optical fibers, where analog Hawking radiation can be coaxed into being, ion traps and superconducting circuits where scrambling and page curves can be imitated, and quantum simulators where entanglement wedges and teleportation through synthetic wormholes move from chalkboard to chip, because when a ledger is too distant to inspect in the wild, the wise course is to build a small one on a bench and learn how to read its pages.